Hello everyone, today we'll talk about the solution to the problem regions cut by slashes. Feel free to pause the video and read this short statement, but as a refresher, we are given a grid where some slashes or backslashes can be placed. So this is an empty space, and this is an empty space. Let's say that those are all empty spaces and those are also all empty spaces, and there are two slashes and two backslashes. So this is a 3-row, 4-column grid. Regions in that grid. So we have one region here in the corner, one region here with this triangle, and the rest of those positions are all regions that are all connected to one big region. And of course what we see here is that it's not like a single square can only be within one region, but it is something similar to it, and the essence of the problem is how to translate this problem to a problem on either a general graph or a problem on grid. So first, when we think about this problem in terms of a general graph, the idea would be to add those small little edges one by one, somehow notice when we create a new region, and when we do create a new region, then we know, okay, a new region was created, we can add it to the result. So this is not the solution I'm going to present today, but to talk about it because it is an interesting solution. The question is, how many regions can be created by adding a single line? And the essence to making this solution doable is the fact that the single line can only create at most one new region, because it can split a single region into two different regions. It should actually be quite easy to see, because if this is the spot where we are placing our slash or backslash, let's say it goes like this, so it's a slash, then the most that it can do is make it so that this big region that contained this square now splits into a region that contains this part of the square, a region that contains this part of the square, but there is no way for more regions to be created as a result of it. And doing it like that, we can keep a DSU, a disjoint set union, to see if two elements are connected. And whenever we add an edge between two elements that were connected before, that means that, for instance, we add an edge from here to here. If those two elements were not connected, then of course we do not create a new region. However, if they were connected, there was some sequence of lines between them, and that means that this thing is a big region, and we split that region in half. So that is a simple solution. This part of proving that this actually counts the number of regions correctly is the most difficult part. So I think it's easier to think about a different solution, about, I think, a cuter solution, because it's a bit simpler. And that solution will be counting those regions as normal. And of course we see here that it's not easy to count those regions just by themselves. In particular, a single square can be in more than one region. However, what we can do at this point is to look at how those regions work. And we can either visualize those regions as split into 4 parts. So now this part will always be a neighbor of the corresponding part on top, this on the right, and so on. And now either all 4 of those are connected as neighbors, or we have a slash, in which case those two and those two are not connected, likewise with a backslash. And I'm talking about connections. You can of course use DSU at this point as well. But an even simpler thing is to notice that while of course a single square here can be part of more than a single region, if we in a sense zoom into the grid enough, if we reduce the resolution or increase the resolution enough, then at that point we can be sure that a single square is either part of the border or part of exactly one region. So for instance, if we were thinking about making it every square a 2 by 2 square, well, that doesn't really work, because it seems like it might work by representing a slash by this checkered pattern, but this doesn't actually work, because we can see, if you try to implement it or if you try to solve it on paper, that sometimes we'll see that two different elements are considered to be in different positions on the grid. So for instance, the simplest way to see it is that if here we have another slash, and maybe here we have another slash, then those three are considered to be different regions because they are not connected diagonally. So we see that 2 by 2 is not enough, but 3 by 3 is enough. And of course, a representation that's 3 by 3 would be, this is a slash, and a backslash likewise rotated 90 degrees, or flipped, however you want to look at it. And in that case, now we do indeed have a correct representation, because no matter how you put them together, it's not possible to get those weird regions, because here we have essentially a 2 by 2 border that makes it impossible to get false positives. So essentially we have to create our grid to be a thrice zoomed out or zoomed in, however you want to look at it, version of our grid. So I suppose in this case it would be zoomed in, but it would be bigger. Transform it, of course, so an empty 3 by 3 square is an empty square from the original array. A slash is something like this, a backslash is the opposite. And now simply count the number of regions in that array, and of course you can still use DSU for it, but you can also use any way you like to search a graph, to search a grid, so DFS or BFS, and just essentially color every visited square to be black. And however many times you have to start with a fresh, unpainted vertex, that's another region. And so let's walk through the boilerplate. Our height and width will be thrice what they should be normally. We create a simple version of the grid. And now we have to transform it to take into account all the slashes and backslashes. So for a backslash, so this is the one that goes on the main diagonal. As we mentioned in yesterday's video, the main diagonal happens in such a way that we start in the upper left corner and we add the same amount to both the row and column to get all the other vertices on that main diagonal. So in particular, if the remainder from the division by 3 is the same for row and column, then they are on the main diagonal, right? Because if here the remainder would be, let's say 0, here the remainder will be 1, and here the remainder will be 2 for both of them. And all the other elements will have different remainders when divided by 3. And of course, likewise for the counter diagonal. Now, it's either remainders are 0 and 2, or 1 and 1, or 2 and 0. And in that case, we just notice that their sum is equal to 2. So that will be for the slash case. And of course, when we divide our row and column by 3, round it down, this is the position on the original grid that we're looking at. In that case, this is an impassable vertex. And we simply create an array of possible directions. This is the number of islands that will be incrementing whenever we see a new island. And now we try to start at every position. So row and column in those tripled values. And now, if we've already visited it, or if it was part of the obstacle, we do nothing. Otherwise, this is a new island. We remember to sync every land tile that we look at. So to mark it as an obstacle, in this case, we keep a list. So this is a DFS. So because a list operates as a stack. And while we have anything on our stack, we take it from the stack, we try to go up, down, left, right, so in every direction. If we're not within bounds, we continue. If this is an obstacle or an already visited tile, we continue. Otherwise, we mark it as visited and add it back to our list. And at the end, we just return the number of islands. So this is a standard number of islands type of question. And this is the only transformation that we really required.